Section 6.4, tangent and secant. All right, last time we did sine and cosine, tangent, the other starter, and then secant, the first guy, first trig function in off the bench. We're not likely to do cosecant or cotangent. Okay, so this is just a general review about vertical asymptotes. Tangent and secant both have vertical asymptotes. So vertical asymptotes typically come about, often through division by zero. So I just wanted to look at fractions where we have something that's very close to division by zero. So I want to look at tiny numbers and not tiny numbers. And it's a vague term, but tiny numbers are just numbers that are very close to zero, and not tiny or not quite so close to zero. So 1, fairly small, but we're not going to call it tiny. The point here, though, is that the sign, the plus minus, doesn't come into whether a number is called tiny or not. Okay, so what we want to look at is how huge fractions come about. And we get huge fractions whenever we have a fraction of the form not tiny divided by tiny. All right, those types of fractions always produce what I'm going to call a huge number. Again, I don't have a definition for huge, but large. So here are some examples. 12, not tiny. Negative 0.003, tiny. So here's the decimal. So 4,000, pretty big. Again, not tiny divided by tiny. And if we go to the calculator, huge, right? Not tiny divided by tiny, always producing these very large numbers. Okay, so we're going to know that not tiny divided by tiny always gives us a big value. But the other thing that we're going to track down here is what's the sign of the huge value? Is it positive or negative? And to do that, all we're going to look at is the sign of the not tiny and tiny. And if they are opposite signs, like in this first example, a positive divided by a negative, then the huge value is going to be negative. If the not tiny and tiny have the same sign, like here they're both negative, the negatives are canceling out and we get a huge positive. Here, opposite signs, we get a huge negative. Okay. Yeah, so I guess this is a test for us. Will this fraction, it's going to be huge, but will it turn out to be positive or negative? Positive over negative, it's going to be a negative. Negative over negative, this one will be a positive, and this one will be a negative. And the suspense is killing me. Negative 1. This times 10 to the minus 6, so this is a million. So negative 1.6 million, and that was a positive 3,000, and this should be a negative 109,000. Okay, so how is this related to asymptotes? Well, going back to something you looked at before, this rational function, a ratio of two polynomials, it's going to have a vertical asymptote where? Well, where its denominator is 0. And its denominator is 0 when x is equal to 4. So what we're going to do numerically is just check for numbers very close to 4. A number that's slightly less than 4 and a number slightly bigger than 4. And we're going to plug them into this function. Right? In the numerator, what I'm going to have is 1 minus something very close to 4. So in the numerator, I'm just going to say 1 minus 4, that's about negative 3. And that's not tiny. Right? Downstairs, the difference between 399 and 4 is tiny. And because 399 is slightly less than 4, 399 minus 4, this is going to be negative tiny. Negative tiny. Right? And so what we just went through is a negative over a negative. This is going to be huge and positive. Right? When I plug in 4, again in the numerator, I'm getting roughly negative 3. It's not a tiny number, so I can just put in the approximation. Downstairs, I'm getting something slightly bigger than 4 minus 4. That's going to be tiny and positive. Right? This fraction is going to come out to be negative huge. Right, what's all this about? Well, we're just trying to figure out how we can predict the behavior of the vertical asymptote based on this hand calculation. So just to the left of 4, when I'm on the left side of x equal 4, the function values, the outputs of f, by my calculation here, we're getting huge and positive. And that's why we're going up the vertical asymptote on the left-hand side. And just to the right of 4, just on the other side of x equal 4, the output of the function, the y coordinates, are getting huge and negative. And that's why I'm plunging downward on this side of the asymptote. Okay, so that was a 5-minute review of asymptotes, vertical asymptotes. And now we're going to look at the graphs of tangent and secant. Okay, so if you remember, tangent is sine divided by cosine. So just like the rational function we were just looking at, the graph of tangent x is going to have a vertical asymptote wherever the denominator is 0. Right? The denominator is cosine x. So the little ghost function I have drawn in here, this is the cosine function. It starts at height 1 and drops down. I haven't plotted it forever, but that's the start of the cosine. I could have gone another pi over 2 maybe, but in any case, what we're seeing is where the cosine is 0, that is at the x-intercepts, where the y-coordinate is 0, the red graph, that's the tangent graph, the graph of tangent, has a vertical asymptote. Right? So it's got infinitely many vertical asymptotes, this tangent, the graph of tangent, one at every odd multiple of pi over 2. Negative 3 pi over 2, negative 1 pi over 2, and so on. Okay, so I just wanted to try this example about predicting the behavior near the vertical asymptotes with the tangent function. So we're going to look at pi over 2 and try to explain why the tangent is going up on the left and down on the right of this vertical asymptote. Okay, so again, what we're going to do is plug in numbers that are slightly less than the x-coordinate with the vertical asymptote, so slightly less than pi over 2, and then something slightly bigger than pi over 2. Right, so down here, pi over 2 plus a little something. Okay, so again, tan is sine over cosine. The sine of pi over 2, that's 1. And because that's not tiny, we're not going to worry about this little 0.001. The sine is, in the numerator, we have roughly something equal to 1. And downstairs, the cosine of pi over 2 is 0. So this is going to be a tiny number. It's going to be very close to 0. But what we want to ask is, when we're slightly less than pi over 2, is the cosine positive or is it negative? Right? So this, you can look on the graph that I'm pointing at right now, or you can think back to the unit circle. If we're slightly less than pi over 2, we're not quite up to the top yet, so the x-coordinate is still positive. Right? So this ratio turns out to be huge and positive, and that's why we're going up on the left side of this vertical asymptote. And I think I'll try to cut this a little bit shorter. On the right side, the cosine winds up being very tiny but negative, and so this fraction becomes huge and negative, and that's why we're diving down on the left side of the vertical asymptote. Okay, right. The tangent function is, like sine, cosine, is also periodic. It repeats, but this is a special thing you have to note about the tangent function. Its period is not 2 pi. From the graph here, we can see that as you go from pi over 2 to 3 pi over 2, the graph is completing one full period. So the period, based on the graph, okay, well, based on the graph, the calculation I just did would be 3 pi over 2 minus pi over 2. This is pi. So that's how long it takes to repeat one period of the graph. So the most common, a lot of code here, the most common period to plot out on is from minus pi over 2 to pi over 2. So this is the graph you'll see for tan x most often. And again, it's just understood that the graph continues to repeat every pi units as you move along. but we don't draw the whole thing, just the one period. Okay. Yeah, so for the tick marks here, to be honest, I should have prepared this. The minus pi over 2 and pi over 2 are really the only x tick marks we expect to see. And then, boy, I'm saying this off the top of my head, I'm close to saying that I don't care about any of the y tick marks. We don't really have any thing to hang our hat on for how high this function should be. Yeah, I'm probably going to regret saying that. Maybe we should put in a tick mark at 1. Yeah, that's what I'm going to do. And forgive me for this quick little change here. Tick marks, do I have them? Let's say minus 1 and 1. Right, let's put in those two tick marks on the vertical. And where should they occur? Those tick marks should be at a point halfway, let's see, halfway between 0 and pi over 2, right here. This is pi over 4. You should go up to your graph, and the tangent of pi over 4 is 1. So then go over here and make your tick mark. Okay. Hopefully we can get that straightened away. All right, graph of secant is the other one for today. And like tangent, the formula for secant has cosine in the denominator. Secant is 1 over cosine. But because of the cosine in the denominator, just like tangent, secant is going to have a vertical asymptote wherever the cosine is equal to 0. Right? I guess we did this before for tangent, but here it is for secant. This time the numerator is just flat out 1. We don't have to estimate it at all. That's the definition of secant, 1 over cosine. When we're slightly less than pi over 2, the cosine is really super tiny, but it's positive, so the fraction comes out huge and positive. And here we have 2 negatives. So again, for the secant, we see it going up the right side of the pi over 2 and down on the left side of pi over 2. Okay. Right, the graph repeats. Maybe I could have plotted just a little bit more of it. And I'm going to make the same quick adjustment here on the y coordinates. Again, I should have had this done in advance. The y coordinates, where are the tick marks? Tick automatic. The only y coordinates that we're going to be interested in are 1 and minus 1. Okay, so when x is equal to 0, we get the secant is 1 over the cosine of 1. Sorry, 1 over the cosine of 0, so it's 1 over 1. The secant function, the low point here is at 1, and the high points here on the downward bowl shapes are at minus 1. So that's why I want to put the tick marks there. Okay. Right, so the period for secant, again, maybe I should have plotted it out just a little bit further. Maybe I can do that now. Hopefully this doesn't crash the machine. There we go. We get this up cup, a down cup, and then an up cup, and it continues to repeat that way. So to go through one repetition, an up cup and then a down cup, well, let's measure. That goes from 3 pi over 2 back to minus pi over 2. So that's a distance of 2 pi between those two. So it repeats every 2 pi units. Maybe I can put in that. Let's do it from here to here, just so we have positive numbers. We'll do a down cup and an up cup. So those go from 5 pi over 2 to, it was 3 pi over, oops, let's not have that right. Yeah, it was pi over 2. And this comes out to 4 pi over 2 or 2 pi. Okay, so where are we going to plot this graph? Well, our book offers up this picture. They say we're going to plot it from 0 to 2 pi. And that is one period. To me, it looks funny in that we're breaking the the upward cup into two pieces. We get half of one here and the other half here. It's totally fine to do it this way. In fact, I'd probably suggest doing it this way, but my personal preference has always been to do this, to plot from minus pi over 2 to 3 pi over 2, because that way the graph only has the two pieces instead of being broken into three pieces. But whichever you choose is fine. I should say, however, that at least this one, it should be on the open interval. Yeah, I'm not going to take the time to, yeah, I guess I should fix this. This would really be, because of the vertical asymptotes, technically we really should be excluding those coordinates where the vertical asymptotes are occurring. To 2 pi. Right, maybe another reason to prefer this plot. Still don't have it right. All right, I'm going to put in a timestamp and then we're on to translations, I think. Okay, only two pieces here. All right, so timestamps. I just said timestamps. 17 minutes. So cosine kx and sine kx, hopefully you remember from last time, is that the period for these two functions is 2 pi over k. And if you remember the yeah, I've got this written once in the box and once not in the box. Okay, so if you remember that sine x and cosine x themselves have period 2 pi, then what I'd like you to think about is rethinking these formulas as simply sine of kx has the period equal to the period of sine divided by k. Okay, so the reason I want you to think in this context is you remember that secant, or you remember, we just saw that secant has a period 2 pi. So we can just add another line to this table. The period of secant kx should be the period of secant divided by k. And again, that's 2 pi over k, because the period of secant is, x is 2 pi. Right? The reason I want you to think about it this way is because now we can extend this rule to tangent, but we need to remember that tangent has period pi, not 2 pi. So this is a rule that allows you to group all four of these things together. The period of trig kx is the period of trig divided by k. Maybe I should make this in bold, bigger, bold, bigger. Okay, so just a quick example here. Periods for these functions. Well, the k is 3. The period for this function, the period for secant is 3. So the period for secant 3x will be 2 pi over 3. Here my k is equal to pi. The period for cosine is 2 pi. So the period for cosine pi x will be 2. Okay. The k in this formula is a half. The period for, and here's the challenge to remember, is that the period for tangent is pi. So when we divide that by the k, we would get 2 pi. Okay, so we'll need that when we do our graph transformations here. So we're doing several combined transformations here. So graph tangent pi over 4 x plus 1. So we deal with the period first. The period, we answer this question by first picking off the k, and then using our new formula here, So this will have period 4. And what's the tick adjustment? Is it, well, we multiply all x, sorry, I'm saying it's the wrong way. We divide all x ticks by pi over 4. Right, there's no amplitude. We would have thought about that first. The shift here is x. The graph is going to be shifted 1 unit to the left. I guess I already said that. And so we will subtract 1 from all x ticks. Okay, so let's do these one at a time. Remember that the graph, well, we just look at it, so let's look at it one more time. Tan x, we usually plot it from minus pi over 2 to pi over 2. I'm sorry, I don't have the correct x ticks there. So I got to put them in. We're going to divide these tick marks by pi over 4, so pi over 2 divided by pi over 4 is 2. That's 4 divided by 2 is 2. So that says the new period is going to go from minus 2 to 2, and that's why I'm plotting that way. So here's tangent pi over 4 times x. And we go from minus 2 to 2. And then the last thing is to do the shift. When we add in 1, when we replace x by x plus 1, the graph is going to get shifted 1 unit to the left. So now the appropriate x coordinates are from minus 3 to 1. And these would be the appropriate ticks then. All right, try one more. So let's try minus 3 sine pi. So the amplitude here is 3. The tick adjustment, you multiply. Oh, geez. Multiply y ticks by 3. To get the period, we first get that the k is equal to pi, and the period, well, the period for secant is 2 pi, so we divide by k to get the period for secant. Pi x is going to be 2. The tick adjustment, this is always the case here. We divide x ticks by k equal pi. Okay, so here's the standard secant, again, pretty new. So look at it again here. We're going to get the graph that we're after, we're going to multiply the y ticks by 3. That'll be the amplitude adjustment. And we're going to divide all of the x ticks by pi. Okay, so we'll be going from minus 1 to 1. And that's what's going to give us the period of 2. Okay. The other thing to note here, though, is that this amplitude, this number a is negative, so the graph is going to flip across the x-axis as we do the sketch. Right. So this is what I'd expect for a level of detail in a hand sketch of y equals negative 3 secant pi x. Okay. Last topic, so I won't bother putting in the timestamp. Again, we're going to do this reverse process where we're given the graph and asked to come up with a formula. Okay, so look at this graph. It reminds me of the secant graph. So we're going to try to view this as some translated secant function. So on the one on the left is we're trying to come up with the formula for. The one on the right, that's just secant x. Okay, so in the graph on the left, the amplitude here, and this is just by looking at the vertical scaling. This is trickier than I thought. I beg your pardon here. This graph has also had a vertical shift on it. I hadn't noticed that. So if we go from the highest point of a downward cup to the lowest point of an upward cup, that distance is 2. So 2 minus 0 is the amplitude. The period, let's see, well, how long does it take to get a repeat here? I guess it's 3 pi over 2 minus a negative pi over 2. The graph is going to start to repeat again as soon as we go on past 3 pi over 2. So this, something's gone wrong. 3 pi over 2 minus a negative pi over 2, that's 4 pi, got that right? Something's looking funny. No, I guess that's right. 2 pi. Okay, so maybe this is the period is equal to 2 pi over k, and so to make it a short story, k is equal to 1 here. Okay, so again, I'm feeling a little bad that I didn't notice that there are 2 shifts going on here. There's both a vertical shift and a horizontal shift. So oh shoot. Yeah, so yes, this amplitude, boy, I picked a problem that was too hard. Oh well, this amplitude is going to be 1. So in the normal secant graph, the distance between a trough, a low point, and a high point is 2. From -1 to 1 is 2 units. And that's the same here. The vertical distance between a high point and a low point is 2. So this has simply had a vertical shift of 1 unit. The horizontal shift is the last thing to get. Now I'm rattled. Horizontal shift. Okay, so instead of being centered on the y-axis, this thing has been shifted pi over 2 to the right. All right, so let's see if we can put all these things together then. So there is no value, or the k is equal to 1. The amplitude is equal to 1. Oh, this is so much not the problem I thought it was. The only difference here is going to be this shifting. So to shift to the right, we're going to replace x with x minus pi over 2. And to shift up, we're simply going to add a 1 onto the function. All right, let's see if I get this right. I think I have it right, it's just I haven't plotted it on the correct range. They plotted from minus pi over 2 to 3 pi over 2. Okay, and the tick marks that I'll put in here are 0 and 2 on the horizontal, or on the vertical. Okay, so I believe that is now matching up. Okay. We'll be sure to do another one of these problems tomorrow in class. I'm sorry this one took a little longer and was a little harder than I expected.